Okay, so this is chapter 12 homework. This is problem 12.7. It says that a tugboat pulls a small barge through a harbor. The propeller thrust minus the drag produces a net thrust that varies linearly with speed. Knowing the combined weight of the tug and the barge is 3,600 kilonewtons, it asks to find the time required to increase the speed from the initial value of v1 from 1 to a final of v2 equals 2.5 meters per second, and the distance traveled during this time interval. So we're given the equation that F is equal to 81,000 minus 27,000 times V. And we can use Newton's second law of force equals mass times acceleration. Now we're given the combined weight is 3,600 kilonewtons. So we're going to bring that unit of force down to a mass. We divide it by gravity, divided by 9.81 to get 366,972.5 kilograms for the combined weight of the tugboat and the small barge. And then we just simply use second law, put in the force value of 8100 minus 2700 v is equal to mass times acceleration, which is dv dt, and then just using separation method and putting in our upper and lower bounds for our v of 1 to 2.5 and our t from 0 to t. We do a little bit of differential equations and some integration to find that our equation is going to be t equals negative m over 27,000 times the ln of 1/4. And then once you plug into 366,972.5 for m and put this into a calculator, you get that t is equal to 18.84 seconds. So that's the amount of time required to increase the speed from 1 meter per second to a final value of 2.5 meters per second. Now the second part is asking us to find the distance traveled during the time interval. So all we have to do is take our AV dv dt is equal to dt equals dv ax, and then we just integrate both sides. Use u substitution. We find out what a is in terms. I didn't do it up here, so I had to find out what a was in terms of the 8100 minus 2700 divided by the 36,000, so we get a is equal to 0.073575, or simply 1 over 0.0735. So once you do some integration and some u substitution, you get that x is equal to 13.575 times 3 minus v minus 3 ln of 3 minus v, and the upper and lower bounds 1 and 2.5. And then once you plug in those upper and lower bounds of integration, you get that the total distance traveled during the time interval is x equals 36.14 meters. Okay, so this is problem 12.2 from the homework. And so this is a 5,000-pound truck being used to lift in a 1,000-pound boulder, here denoted by B, on a 200-pound pallet, here denoted by A. It says that the acceleration is 1 feet per second squared, and asks to find the horizontal force between the tires and the ground and the force between the boulder and the pallet. So we know that the acceleration of the truck is 1 meters per second squared. That means the combined acceleration of both the rock and the pallet has to be 1. So we just give half a meter per second squared to each one. And then I simply just converted the weights over to masses for the truck, the boulder, and the pallet. If we just look at the free body diagram of the boulder, the pallet, and the pulley system here, and we some moments about this point 0, we can find that T2 is equal to T1, and then so we form some forces in the y direction, and we get that 2T2 minus the mass of A plus the mass of B times G is equal to 0. Solve for T, and we get T is equal to 609.32. Now we just we cut the free body diagram here, and now we have the tension force. We found 609.32, and we just use Newton's second law again. So the forces of the truck is equal to the mass times acceleration times t. Mass times acceleration of the truck. And plugging in our nodes, we find F, which is once again the horizontal force between the tires and the ground. And plugging in our nodes for t and the mass of the truck, which as we found earlier here, be 155.28 slugs, and then the acceleration was given to us as 1 feet per second squared. We find that the horizontal force is 765 pounds. Now the second part of the problem is asking to find the force between the boulder and the pallet. So then once again, we just go back to the free body diagram of the boulder and the pallet itself, and we use Newton's second law: force equals mass times acceleration. So we just have that in the vertical components, um, you have the force of the pallet, which is like the normal force, minus um, the force of the of the rock, which is the mass of the rock times gravity, is equal to the mass of the rock times acceleration of the rock. So we know the acceleration of the rock is going to be 0.5 feet per second squared, and we know the mass of the rock, which was found here, is 31.056. And so we just isolate our unknown, which is our normal force, or the force of AB, and we plug in our knowns, and we find that our force of AB is 1,016 pounds. Okay, so this is problem 12.36. It says that a 450-gram tetherball A is moving along a horizontal circular path at a constant speed of 4 meters per second. That's to find the angle theta that the cord forms with the pole BC and the tension of the cord. So I went ahead and drew the free body diagram of just the ball. So we have that there's a force of the M2, the mass of the ball times gravity, and the tension force here. So we sum forces in the y, we get that the t cosine of theta is equal to the mass of the ball times gravity. Solve it in terms of t, we get the mass of the ball times gravity over cosine of theta is equal to t. Now we sum forces in the x, we get that t sine theta is equal to the mass of the ball times the acceleration of the ball. And the reason why is because it's going along a horizontal circular path. We know the acceleration that it's feeling is centripetal. So we can rewrite this as t sine theta is equal to the mass of the ball times v squared over rho. Now we found originally when we sum forces in the y that t is the mass of the ball times gravity over cosine of theta. So I simply substituted that value in here. So this is t sine theta is equal to the mass of the ball times v squared over rho, where rho is 1.8 sine theta. So the rho is just this distance. So 1.8 sine of theta gives you this distance, which is your r value. Cross out like terms, and then you're getting sine squared of theta over cosine of theta is equal to v squared over 1.8g. We'll go back to our trigonometry properties. That sine squared of theta is equal to 1 minus cosine squared of theta, so we substitute that value in. So 1 minus cosine squared of theta over cosine theta is equal to 4 squared over 1.8 times 9.81. And then we just simply solve for theta using the quadratic formula, and you get that theta is equal to 49.9. The second part is asking us to find the tension in the cord, and we know that T is equal to mbg over cosine of theta. The only unknown we were missing before was theta, but now we found it, so we just plug in our knowns, and we get the tension in the cord is 6.85 newtons. Okay, so this is problem 12.44. It gives us that there's a 130-pound wrecking ball that's attached to a 45-foot long steel cable, AB, and it swings the vertical arc. It asks us to find the tension in the cable at the top C of the swing, and at the bottom D of the swing, where the speed of the wrecking ball is 13.2 feet per second. So looking at the free body diagram of when it's at C, we know that this angle here is 20. It's given to us, and we know at C, the velocity is going to be 0. So the acceleration of centripetal is going to be v squared over r. We know the velocity is going to be 0. Therefore, our acceleration is going to be 0. So we sum forces in that direction, the centripetal or n direction. We can see that t, this way being positive, t minus the w cosine of theta, which would be here, is equal to 0, because using Newton's second law, it would be mass times acceleration. We found earlier that the acceleration is going to be 0. So t minus w cosine of theta is equal to 0, and therefore the tension is equal to w cosine theta. Plug in our knowns, and we get that t is equal to 122.2 pounds. Now it's asking us to find the tension in the cable at the bottom D of the swing, with speed of B is 13.2 feet per second. So here's a free body diagram of it at D. where the weight's completely down and the tension is just going straight up. And that is equal to the mass of the ball times the acceleration, which is centripetal, since it's going to be, moving that way. The acceleration is going to be feeling it's not tangential, rather centripetal. We know once again that the acceleration due to the centripetal acceleration is v squared over r, where r is that is given. It's the 45-foot long steel cable AB. So plugging in our nodes, we get, using sum of forces in the y to get all our forces, we get T minus W is equal to the mass, and this is given to us as a weight, 130 pounds. So we have to divide that by 32.2 times acceleration, which once again is v squared over r, where v is 13.2, and that was given to us, and divided by the r, which is 45, and we get that T is equal to 145.6 pounds. Okay, this is problem 12.57. It gives us this image of a turntable A, and that the trunk B starts to slide on the turntable 10 seconds after the turntable begins to rotate. Knowing that the trunk undergoes a constant tangential acceleration of 0.24 meters per second squared, it has to find the coefficient of static friction between the trunk and the turntable. So knowing that the trunk undergoes constant tangential acceleration, we can use the kinematics equation of v equals v naught plus at to find our final velocity, which is going to be 2.4 meters per second. Now, if we sum forces, if we use the free body diagram of B, we know that it's experiencing just the frictional force, and that is equal to the mass of the trunk times the acceleration. It's experiencing both a tangential and a centripetal acceleration, and so we have to find the net resultant of those two. So if we write this stuff out, it's F equals the mass of B, which is the trunk, times the acceleration tangential, plus the mass of B times the acceleration centripetal. So taking the net resultant of those two, we have to square them both and take the square root of it. And then looking at the free body diagram of just the trunk itself, we have the normal force, the weight, and the friction. So if we sum forces in the y, we get that then the N is equal to W. So the normal force is equal to W, where W is equal to, so the N is equal to mb, the mass of the trunk, times gravity. And we know that the frictional force is mu sub s times n. So we plug in what we found for n here, and we know that the frictional force is mu sub s times the mass of B times gravity. So plugging this in, and over here where F is equal to this, we get that the mu sub s times the mass of B times gravity is equal to the mass of B times the net resultant of these. And then we plug in our knowns, where we divide out like terms, so the mass of the trunk goes away, and divide over the gravity, and plug in our knowns. So our acceleration tangential was given to us as 0.24 squared, and then our centripetal we know that is v squared over r, or v squared over rho, and that distance is given to us as 2.5 meters. And we know that at 10 seconds, we found that the velocity would be 2.4 meters per second. So plugging all that stuff in, we get that the friction between the trunk and the turntable, the coefficient of static friction between the trunk and the turntable is going to be 0.236. All right, so this is problem 12.82. Gives that the orbit of planet Venus is nearly circular with orbital velocity of 126.5 times 10 to the 3rd kilometers per hour. Gives the mean distance from the center of the sun center of the sun to Venus to the center of Venus being as 108 times 10 to the 6 kilometers. So that's the that r, and the radius of the sun is 695 times 10 to the 3rd kilometers. Asking us to find the mass of the sun and the acceleration of gravity at the surface of the sun. Um, so we can use Newton's law of universal gravitation here for the force. We know the force is equal to G m, big M, little m, over r squared, and then use Newton's second law to find out the solution. So using the force is equal to mass times acceleration, where the acceleration is v squared over rho. We can get rid of like terms and write it in terms of m, big M, which is the mass of the sun. So the mass of the sun is equal to rv squared over g. And then I went ahead and changed all the units into the ones we're supposed to be using. So meters and meters per second for both the radius, because this was given in kilometers, and then this one was given in kilometers per hour. So just a simple conversion to change both to meters or meters per second. And then went ahead and plugged in our known values, G being the constant as well, and find that the mass of the sun is 1.998 times 10 to the 30th kilograms. The second part is asking for the acceleration of gravity at surface of the sun. And then once again, we just use the same expression, force equals mass times acceleration. But this time we use the radius of the sun, and we're using the acceleration is due to gravity. And it's again asking us to find the acceleration of gravity, so we just divide the small m over, which gets rid of it. So all we have is the g, the constant, times the mass of the sun, which we found earlier here, divided by the radius squared, which was given to us in kilometers, and convert that over to meters, and we end up finding that the gravity, acceleration of gravity at the surface of the sun is 276 meters per second squared. Okay, this is problem 12.94. It gives this diagram. This is the particle mass m is projected from point A with the initial velocity of v naught, and it's perpendicular to OA and moves under a central force F along an elliptic path defined by the equation r equals r naught divided by 2 minus cosine theta. It gives us to show that F is inversely proportional to the square of the distance r from the particle to the center of the force O, which is here. It gives us a hint of using the 12.35 equation, which is the second derivative of u with respect to theta plus u is equal to the force, or F, over mh squared u squared. And it gives us that u is equal to 1 over r. We're given that r is equal to r naught over 2 minus cosine theta, so we take the inverse of that to get u. And then we take the second derivative, take the derivative twice to get d2u over d theta squared, which equals cosine theta over r theta. We plug that back into our original equation here and solve for f, and we get that f is equal to 2 over r theta mh squared u squared. But u squared is nothing more than the 1 over r, so we can rewrite this as f is equal to 2 mh squared over r theta divided by r squared. And we know that m, h squared, and r theta are constants, so f is proportional to 1 over r squared. Okay, so this is problem 12.104. It gives this diagram, and it's asking us to find the increase in speed required at point A for the satellite to achieve the escape velocity and enter a parabolic orbit. And it's also find the decrease in speed required at point A for the satellite to enter an elliptic orbit of minimum altitude 6,370 kilometers, and then also see the eccentricity of the elliptic orbit. So using Newton's second law, force equals mass times acceleration of gm, small m over r squared equals mass times gravity. And taking out like terms, we can get that the gm is equal to gr squared. We solve for gm, plugging in our known values of gravity being 9.81, and then our r is given to the 6,370 kilometers. So we just have to multiply that by 1,000 to get into meters, and we get that gm is equal to 398.06 times 10 to the 12th meters to the third divided by second squared. We know the escape velocity and the velocity of the circle equation. So the velocity of the circle equation is the square root of gm over ra, and we just plug in our known values. where RA is once again the radius, so we just add the radius of the Earth, and then this distance here, and we get that the radius of A is equal to 25.48 times 10, 25.48 times 10 to the 6 meters. So plugging in our knowns into the equation of the velocity of the circle, we get that the velocity of the circle is 3.9525 times 10 to the 3 meters per second. Now the escape velocity is going to be the square root of 2 gm over RA. We already found the square root of gm over RA to be 3.95. So we just multiply that by the square root of 2, and we get the escape velocity to be 5.5897 times 10 to the 3 meters per second. So therefore, the increase in speed is going to be the difference between the two of the escape minus the circle velocity, and that'll equal out to 1.637 times 10 to the 3 meters per second. The second part of the problem is asked to find the decrease in speed required at point A for the satellite to enter an elliptic orbit of minimum altitude. So we know the radius of B is going to be 6370, which is the radius of the Earth, plus this distance here, right? It's because we want this distance here and also this distance here. So the radius of B right here is going to be the combined radius of this, and then the radius of A is going to be 6370 plus this value here, 191,110 kilometers. And knowing that it's an elliptic trajectory or elliptic orbit, we can already find that the relation derived is going to be 1 over R naught plus 1 over R1 is equal to 2 GM over H squared. And solve for H, and then plug in our knowns, and we get that our H is 82.28 times 10 to the 9 meters squared per second. And then we plug it into the equation of VA equals H over RA, and we get that our velocity of A is going to be 3.22 times 10 to the 3 meters per second. So the change in velocity is going to be our answer for B, which is going to be the decrease in speed required at point A for the satellite to enter an elliptic orbit of minimum altitude. So we just take the velocity of the circle found earlier minus the velocity at A found here. We find that decrease in speed is going to have to be 725 meters per second. For part C, it asks us to find the eccentricity of the elliptic orbit, and we just use the relations once again. 1 over RB minus 1 over RA is equal to C cosine of theta B minus C cosine of theta A. And we solve for C. So we get C is equal to RA minus RB over 2 RA RB. And then we just plug in our knowns, which is radius of A, radius of B, which we found earlier. Subtract the 2 times the radius of A times the radius of B. And we get that C is equal to 19.623 times 10 to the negative 9 over meters. And then by the equation in the textbook 12.40, we get that the eccentricity is equal to C H squared over GM. We found what GM was earlier. We just found what C was here, and we found what H was in the previous part of the problem. So we plug in our knowns. We find that our eccentricity is 0.333. Okay, so in this problem we're giving this diagram, and it's asking us to find that the circular of the orbit, each of these points can be expressed as 1 over rho is equal to 1/2 times 1 over r naught plus 1 over r1. And then this satellite is an elliptic orbit. So knowing that it's an elliptic orbit, we can use the equation here and try to derive it, or just know that since it's an elliptic orbit, that the relation derived is going to be 1 over RA plus 1 over RB is equal to 2 GM over H squared. Then we can use some of the forces to use second law to make this relationship. So gm m squared over r squared, the force is equal mass times acceleration. The acceleration it's feeling is going to be centripetal, so we can rewrite that as v squared over r, or v squared is also can be rewritten as h squared over r squared times 1 over rho. So that's what I did here. And then canceling out like terms and dividing over the h and canceling out the r squareds, we get that gm over h squared is equal to 1 over rho. But if we look at this expression, it says 1 over rho is equal to 1/2 of 1 over r naught plus 1 over r1. And this is saying gm over h squared. But if we look at our original relation derived of 1 over ra plus 1 over rb is equal to 2gm, we see that this is sort of the same thing. It's actually just half of this. So if this is half of this piece of the equation, then we can also say this piece is half of this piece of this equation. So we can rewrite this as 1 over rho is equal to 1/2 of 1 over ra plus 1 over rb, which does indicate that the curvature of the orbit of each of these points can be expressed as 1 over rho is equal to 1/2 times 1 over r naught plus 1 over r1.